Welcome, everyone. All right, so for today, we're going to continue on with our direct comparison test to determine whether a series is convergent or divergent. So let's just kind of review over first what the test says, just to kind of refresh our memories. So we have some series, sigma an, that we don't know anything about. We want to see if this is the one we want to see if it's convergent or divergent. And the idea is step one, we find a comparable series, which we call sigma bn. And this is something that we do know whether it converges or diverges. And in order to use this test, the necessary condition is they have to have positive terms. So all the terms, an and bn here, they all have to be positive or at least eventually positive. So if we go far enough in the list of terms, eventually we hit a point where from then on, all the terms are positive. All right, so we find our comparable series and we check our necessary condition. Usually this is more of just saying that all the terms are positive. Sometimes there's a little bit more there that we got to do. And then based on what we know about our comparable series, whether it's convergent or divergent, there's an inequality that we have to prove. And in the case of sigma bn being convergent, we want bn to be greater than an, because it kind of forces an to converge. And in the case when sigma bn diverges, we want bn to be less than an. So we prove the inequality there. And then last step is we state our conclusion. All right, so let's try another example. And again, we're always, for these comparison tests, we're always usually going back to geometric and p-series. So we want to keep these comparable tests in mind. And I guess one other thing to mention is these tests, even though they're, I think, stated with n equals 1, yeah, we don't even specify here. Usually we're talking with n equals 1 as our starting index, but they also work for n equals 0 and really any starting index there. Okay, so just a little bit of the semantics out of the way. So let's look at example 2. So we want to figure out if this series converges or diverges. And we're looking at the sum from n equals 1 to infinity of 3 over 2n squared plus 5n plus 1. All right. So first step is we got to find our comparable series. And to do this, this is where we look at the dominant terms. Usually we're dealing with fractions here. So we look at the dominant terms in the top and the bottom. And in this case, well, 3 is the only thing in the top, so we're going to use that. And then the dominant term in the denominator there is, well, the biggest power of n, so the 2n squared term. So our comparable series in this case, we'll call it sigma bn for short, but this is going to be the sum from n equals 1 to infinity of 3 over 2n squared. And when we look at this, what we have, this is a p-series. This is a constant multiple. We have this constant multiple 3 over 2, but we're just multiplying a p-series here. So this is a convergent p-series with p equal to 2. And if we remember, the p-series converge when our p-value is greater than 1. Okay, so first step is we find our comparable series, usually by looking at the dominant terms, and then we actually have to state whether it converges or diverges, and then we have to give a little reason. And usually this is just saying, you know, it's a p-series with the p-value or geometric series if it's a geometric series. All right, so now we go to our necessary condition. And in this case, we need all the terms to be positive. And they are. So for this test, we need all the terms to be positive. And if we look, let's call this original series sigma an for short. So in the original terms, everything, n is greater than or equal to 1. So all the terms here are all positive. And then same thing in bn. We have 3 over 2n squared. Everything's positive. So we just want to state those necessary conditions. And now we want to prove the inequality. All right. So what inequality do we want to show? Well, we found our comparable series and we're suspecting, well, we know that our comparable series here is convergent. So if we go back up to our test, when we know sigma bn is convergent, the inequality that we want to show is that an is less than or equal to bn. So let's prove that. So we want an less than or equal to bn. So this is what we want to prove. So let's fill in what the terms are. So an is just the term from our original series, so 3 over 2n squared plus 5n plus 1. And bn is 3 over 2n squared. Okay. Now at this point, we're not sure if this is true. This is what we're trying to prove. And even at this point, maybe not altogether obvious. So the idea is we want to work with this inequality and we want to simplify it down to a point where we end up with something that is obviously true. So when we're working on this one, we can, the 2n squared plus 5n plus 1, this is positive, so I can multiply both sides of this inequality by that. Effectively we're kind of cross-multiplying. Same thing with the 2n squared. 2n squared is positive, so I can multiply both sides of the inequality by 2n squared. And when we do that, we end up with 6n squared is less than or equal to 6n squared plus 15n plus 3. And we're getting down to a point where this is, kind of obviously true. Because at this point we have one number here, 6n squared, and then that exact same number shows up on the other side, but then we also have some extra stuff that we're adding. So this is true. And because this last statement is true, that means this statement is true, which means the original inequality is true. So we can eliminate those question marks. So we've proved that inequality. And if you wanted to go a little further, maybe you're not necessarily convinced, you could subtract 6n squared from both sides, and then you end up with 0 is less than or equal to 15n plus 3. And because n is greater than or equal to 1, well, that's definitely true. Okay. So now that we have everything, now we just state the conclusion. We've done it all. And so we can say then, since sigma bn converged, and we prove that necessary inequality for all n, that tells us that sigma an converges by the direct comparison test. And just abbreviating there. But whenever we prove something, prove a series is convergent or divergent, we want to state the name of the test that we used. Okay. So let's try another one. See how this, get a little extra practice here. And we'll look at example 3. So for this one, we want to determine if this series is convergent or divergent. And when we look at this, kind of looks like a geometric series, but not quite. So it's not quite written in that form, and most of the terms have n in the exponent, but we do have this minus 5. So that minus 5 makes this, it's not technically a geometric series, but it is similar to it. So our first step here is we're going to figure out our comparable series. So we'll call this one just sigma an for short, and then we'll call our comparable series sigma bn. And when we do this, again, we want to look for the dominant terms in our fraction. So, the terms that kind of take over when n is getting large. And in this case, it's those, the parts that look geometric. So our comparable series here is going to be n equals 0 to infinity, 3 to the n plus 1 over 2 raised to the n. And maybe the only thing we do just to really make sure that this is a convergent geometric series is we rewrite this just a little bit. So I can break off one copy of 3. So I have n copies of 3 plus 1. So I'm just going to take one of those, kind of break it off, put it first, and then I can separate out and have 3 over 2 all raised to the n. So maybe you show a few more steps here, but this is what we practice for geometric series. And what we see here is now this is definitely written in the form of a geometric series, and it's a divergent geometric series. So again, when we find this comparable series, we just want to state, is it convergent or is it divergent? Our R value here is 3/2, and that satisfies, for a geometric series, we need the R value to be greater than or equal to 1 in order for it to be divergent. Okay, so we know this comparable series is divergent. All right, so next step, we just want to double check our necessary conditions. And that is all the terms are positive. Now, for our comparable series, all of the terms here are positive. We just have powers of 3 and 2. So those are positive. Now we do have some subtraction down here, which does present an issue because when n is 0, we have 2 raised to the 0 minus 5. That's negative 4. And when n is equal to 1, we end up with 2 raised to the power 1 minus 5. That's negative 3. And when n is equal to 2, we end up with 4 minus 5, which is still negative 1. But then once we hit n equals 3, then we're okay. This 2 to the n power does get bigger than 5. So all terms, an and bn, are positive for n greater than or equal to 3. Okay, so, and that's perfectly fine. It's okay that the first few terms, there were some negatives there. Again, the test still works. If we go, maybe there's a few terms at the beginning where there's an issue, but there's a point where eventually from then on, all the terms are positive. We can still use this test then. Okay. So our necessary condition is satisfied. Now we want to prove our inequality. And for our inequality, the inequality we want to prove here, we know our comparable series is divergent. So again, to kind of help us remember, let's just go back to the statement of the test. And when we know our comparable series is divergent, we want that the terms in our divergent series to be less than the other series. That way this kind of like, I think it almost like a wedge, kind of wedges these to be divergent as well. Okay, so that's the inequality we want to prove. That Bn is less than or equal to an. So again, we don't know this yet. This is what we want to show. So first thing, let's write out what each of the terms are. So Bn is 3 to the n plus 1 over 2 to the n. And I'm using the kind of the unsimplified version there. And we want to know if this is less than or equal to 3 to the n plus 1 over 2 to the n minus 5. And we just want to simplify this down to a point where we get something that's obvious. So again, this is not, we don't know this yet. We want to prove this. All right, so what could we do? Well, first of all, both sides have a 3 to the n plus 1 on them. So we can divide both sides by 3 to the n plus 1. And when we do that, we get 1 over 2 to the n is less than or equal to 1 over 2 to the n minus 5. And then from there, we can cross multiply. And as long as the terms we're kind of multiplying are positive, then this is going to be true. Then we can do it. It doesn't change the direction of the inequality. So if we multiply both sides by 2 to the n, I'm going to get 2 to the n on the right-hand side of our inequality. And if I multiply both sides by this 2 to the n minus 5, I'm going to get that onto the other side. And we get rid of the fractions. Now, technically, this only worked when n is bigger than 3. Because when n is less than 3, this is a negative number. And that actually changes the direction of the inequality. So this only works when n is greater than or equal to 3. And then at this point, this is something I would consider obviously true. So what do we have? We have the same number shows up on both sides, but then on the left side, we're subtracting a little bit from it. And if you really wanted to be precise here, you could even go a little bit further and say, well, subtract 2n from both sides, and then you end up with negative 5 is less than or equal to 0. So there you're really good. All right, so in any case, we ended up with an obviously true statement, and all of these are equivalences. So if this is true, well, that means this one was true, which means this was true, which means what we were trying to prove is true. True statement. Again, with this little extra wrinkle there that n had to be greater than or equal to 3, but that's okay. And so now we're ready to just state our conclusion. So that's the last step of this. Just make sure we kind of formalize everything. So our conclusion is, since the comparable series sigma bn diverged, and bn is less than or equal to an, what this tells us then is sigma an diverges by our direct comparison test. So we're able to state our conclusion. And again, just state the name of the test. All right, so this is going to do it for our direct comparison, but we're also going to be looking at the next test is our alternating series test. So I'll see you over there.